In the previous video we talked about church numerals. We know that we can encode any natural number just having pure lambda calculus. We don't need nothing else. When we have these natural numbers encoded in lambda calculus, actually the church numerals, how can they do the simple calculations this? How we can add some operation on these numbers? The simplest thing which we can do is to implement the +1 function. So we have some number and they just add 1 to it. How can they achieve this? Actually, this is achieved by this expression. What's happened here? Actually, this is the +1 function. This function has some n on input. This is the number. Okay, you see here in the notation. Also, this function it's take a number and it needs to provide a number. And we know that in church encoding in church numerals, every number represented as some lambda term, which have the two input. Actually, this term encode a function which have this is a high order function and it has two arguments, the function and the argument. And here we provide this thing, the function and the argument, these two things, this lambda expression. And in the body of this expression, what they do? They take this number, apply to it f and x. What happened then they apply to the number f and x? It will eliminate the outmost part of the lambda expression and we go inside of this body. And this body actually represented this church numeral. We have this function application f n times. And what we do? We just want to add some f. So we add it and add here again our eliminated here the signature of our lambda function. And we're done. Actually, we have the next number in our church encoding. And we can check how this works. I do the video about lambda calculus calculator. And now we can, I think, just take this expression from here. I think it's not copied. But anyway, we can go to this calculator and provide some. Here we can encode our successor function like this. We can say that we have successor and it is represented as a lambda term. Or this lambda term, what it takes? It takes some number. After this, it must return to us some signature which represent the number in the church numeral, and this means that it need to take f and need to take x. What we do after that? We do the application to the number f and x. And then we have this. We need to add 1 to it. So here we eliminate, and here we add, and here we add the signature, eliminate the signature again. Okay, and something like this. Let's try to provide it to calculator, and you can see it done. Actually, we can now use our successor function for some church numerals. And you can see here that this calculator actually encode has numerals representation here. For example, it has 1. Yes, you can see that it encode this number in church numeral. This, and it has 2. But what if I want to take, for example, successor of 2, of 1? And you can see here that actually they have some problem here because I think I don't put spaces here. So I think that this is one argument here, but also I don't want one argument here. I need to provide more arguments. So actually this thing I think need to look like this. Okay, and this will be the successor function. Now let's try to build a successor of 1. Alias not found because it represents like this, I think. Yes. So you can see here that if I provide to this successor function the 1 number encoded in a church numeral, we have some reduction steps, and they finish with this lambda expression, which encode the number 2. And of course I can do the successor of 2, of 3, and so on. Okay, we're done. But this +1 very simple. Let's do something more complex. How we do plus? Let's look here. So this is actually the encoding of the plus function in lambda. And it is very obvious that it is take two numbers, m and n. We want to add two numbers. And as the arguments provide these two numbers. After that, they need to return the number. And they know that the number in lambda calculus starts with f and with the x, and they provide it here. What they do next? Next, they do the simple thing. We just strip our n number. They remove the lambda signature from it by applying f and x. Actually, what we will receive? We will receive the n times of f. So we f n times. And what we want to do next? We want to add to this f n times. We want to add to it f m times. And how we do this? We push this strip part to the m number. Of course, we push to it f at first, but then we push this as argument this n times of f, and actually all this thing m will reduce to f, which has times of m plus n, because at first we have this m, f of m, and then n f of n. And that's all actually. This is the plus. Okay, let's look at how we can do this in our lambda calculator. Okay, let's go here and define the let plus function like lambda expression, which we have on this wiki page. So that it takes some number m, it takes some number n, and it takes some no, actually after this is go the the part which we want to return. And we want to return f, k, and x. So these, if you look at this church encoding, you can see here. It's the signature of this lambda expression, outmost lambda expression. And after this, they need to provide the body. Actually, the body there provide the process of how we do the evaluation, do the beta reductions, and how we define. So, as I said, at first they need to strip our n. How we strip it? We just apply f index to it. After they do this strip of n, we want to push this f inside of m, and they do this by providing to m f, and after this f n times, which are actually represented in this parenthesis if they do all the beta reduction steps. And that's all. This is, I think this is the plus. Oh, I do some syntax error here. Oh, of course, here in lambda notation, I have no equal sign, I have this dot. In the formal language, I have this dot. Now let's check this. Yes, it's done. And we can now test how this works. For example, I want to do the plus of 0 and 1. What I have? I have 1. You can see here all these reduction steps. And if I do, for example, 2 plus 1, you can see that I have this 3 here. And so on. I can do as many numbers as I want. For example, if I add 5 and 3, I will receive 8. Okay? So actually you can play with this and ensure that this plus function works as expected.